All right, we are starting section 3.2 today. We will continue section 3.2 on Monday next week. 3.2 is about linear functions. Our objective is to identify linear functions. Anybody need more time getting their objective down? All right, in that box there underneath lesson, a linear equation in two variables, we usually use x and y, can be written in the form y equals mx plus b, where m and b are constants. What does it mean to be a constant? What would it not do if it's a constant? It wouldn't change. So constants don't change. So if you need that reminder, constants do not change. A linear function has a few components to it. It has a graph that is a non-vertical line. So if it is a vertical line, it goes straight up and down. We don't consider it to be a linear function. It has a constant rate of change. That means the x's and the y's change at the same rate or the same pace. And it can be represented by a linear equation in two variables. A nonlinear function does not have a constant rate of change, and it would have a graph that is not a line. So our goal today is going to be to tell the difference between linear and nonlinear functions. Sometimes that'll be really quick and easy. Other times we might have to think about it a little more. Questions, concerns, need more time on this slide? All right, then we'll keep moving. These graphs are already printed in the note packet, so we have to decide, is it a linear or a non-linear function? What do we think about 1a? Non-linear. Okay, clearly it curves around there. It is not a straight line. That is non-linear. What about letter B?
Linear.
This is linear. It does form a straight line. Okay, it's really easy when you have graphs to decide linear or nonlinear. Questions about examples 1, A, and B? All right, the next set gets a little bit more interesting. We are given a table of values and asked if it's linear or nonlinear. Now, one way you could do this would be to treat all of these as points and graph them and then see if it makes a straight line. But that's going to take a little while to do. Let's see. Your first one shows up as A?
Yeah.
Okay. Is B on the back?
Yeah.
Okay, so we'll just do them in order that you have them. So I'll do this one first. Whoever copied these over into the notes didn't copy them in order. It's fine. All right, so let's start with letter B. Again, we're not going to go through the process of graphing these because, first of all, we'd need a big graph if that goes all the way to 35. And we can just look at how our variables are changing instead. So let's first look at the x's. How are the x's changing? They're going up by 2, right? We're adding 2 every time. And what about the y's? How are they changing? Well, let's go in order. How do we change to go from 2 to 9? We added 7. What about 9 to 20? Dominic?
11.
We add 11. And what about 20 to 35? We'd add 15. So is it changing at a constant rate? No, both the x's and y's would have to change constantly. The x's changed by 2 every time, but since the y's didn't change by the same number every time, it's going to be nonlinear. The x's and y's don't all have to change by the exact same number, meaning these wouldn't all have to be plus 2's down here, but they would all have to be plus 7's, or they'd all have to be plus 11's, or minus 7's, or minus 11's. Okay, so the x's and y's have to change constantly with each other. So your letter B, which would be my letter A, I believe, is that correct? Okay, how are the x's changing? Okay, we're adding 3 to our x's. How are the y's changing? Minus what? Minus 6. So are they changing constantly? Yeah, both the x's and the y's are changing constantly with each other. So this would be linear. Questions, concerns? Ready for the next two? Okay, did these ones go in order? I think they did. Looks like it. All right, on letter C, how are my x's changing? Adding 1. And what about my y's? So what would we say about this one? This one is also considered linear. All right, on letter D, how are my x's changing? Plus 1. How are my y's changing? So minus 8 for the first one, but what about the next one? And then,
So it is nonlinear.
so it would be nonlinear. Very good. They can still be functions. Okay, it's just that these ones are nonlinear versus linear. Questions, concerns about these, Janaya? So a function is what we covered in 3.1. So if it's a function, it's going to have different x values every time. We can't repeat an x value.
Like you could have like 2 strings or something.
Right, so like if they were to have a table that then extended out and said 4 also could go with 0, then it would no longer be a function because 4 went to 2 and went to 0, and that can't happen.
So the x's can repeat, mean the y's can repeat?
The y's can repeat, x's cannot. That was in 3.1. Jada, let's wait till after next. Okay. All right, questions about those examples? All right. All right, for the next set of examples, we are asked which ones would represent linear functions, and we are asked to explain why or why not. So, we could do this in a couple different ways. One of them would be to try to plug values in and see if we can make a little table like we had above. We could potentially graph some of these and look at what the shape of the graph is like. We have some options. We would just have to explain it. So for the first one, y is equal to 3.8. Anybody have any guesses about if they think this would be linear or nonlinear? So let's look at a graph of it. Let's see what a graph of this would look like. I will pull one up. Lucky for us, Google likes to graph things. So let's take a look. This blue line that Google is showing us is y equals 3.8. So would we say that that is linear? Yeah, that's a straight line, right? We said it could be a non-vertical line. That line is not vertical, it is horizontal. So I would agree that that would be considered linear. Okay, so if we are at this one, I would say that this one is linear. You could write by it that it formed a horizontal line when we graphed it. We'll talk more about these types of functions or y equals lines later on this chapter. Okay, questions about that first one? Okay, let's go to the side next to the y equals 3 to the x. And while we could graph this one, I want to think about using an xy table like we just saw, so that we can think about this a little bit differently. Okay, so I could plug in, for example, the number 1. 3 to the first power. Does anybody know what that is? 3. It's just a 3. I could plug in a 2. So that would mean it's 3 squared, or 3 to the second power. 9. So that means 3 times 3. Okay, we could plug in a 3. 3 to the third power is 3 times 3 times 3.
18.
What is it, Austin? 27. 3 times 3 times 3. So let's just look at what we have here. How did my x's change? What did I do? I added 1 to my x's. How did my y's change? What did I add here? And then what did I add next? So is this going to be linear? No. If your x is in an exponent, it will not be linear. So if you want to write yourself an explanation, x in exponent, that will always be nonlinear. Questions about y equals 3 to the x? Okay. For y equals the square root of x. Let's look at another graph for this one. Did we get the first two down? Because the writing's going to go away when I pull up another graph. Okay, so let's do another graph on this one. Bring it over here. Okay, this is the graph for y equals the square root of x. Would we say that this is linear? No, this is definitely not linear. We can see that this line curves around. Okay, so if we bring back our notes slide, we can fill in that this one is going to be nonlinear. What is special or different about this problem that you think made it nonlinear? What symbol? It's not a division sign exactly. What? Liam? The square root symbol, we call it a radical. So if we are underneath a radical, we have a variable under a radical or a square root symbol, it would be nonlinear. It's kind of like an exponent of sorts. So this one is nonlinear, and if you just want to like circle the radical or write down x is under a radical or under a square root. Janaya?
So every time something is like a radical sign or like a 3x sign, is it like automatically nonlinear?
If it's the variable that's there. So yes, so if the variable is in an exponent or the variable is under the radical, That's true. So if we were to have a totally different problem like this one, if we put a radical over that 3.8, that would still be linear. It's just going to be in a different position because we just had a number under the radical, not the variable. Does that make sense? Okay. Good question. Other questions? Okay. On this next one, let's do another table. We'll pick a few numbers to plug in. So if I want to plug in -1, 0, and 1, how are my x's changing? I'm still adding 1 to my x's. So I want you to figure out what the y's would be by plugging those in and tell me if you think it's linear or nonlinear. All right, so what did we get for y when we plugged in a -1 for x? Nobody did it?
Nope. I just think that is linear.
Okay, then we'll do it together. Y equals 6 times -1 minus 1. By our order of operations, what happens first? In the parentheses, -1 minus 1 is -2. Those parentheses now mean that I have to do what? Multiply. 6 times -2 is? -12. Okay, then I plug in a 0. Close.
4.
We would get a -6. 0 minus 1 is -1. Times 6 is -6. What about when I plug in a 1? What's 1 minus 1?
No, what? 0.
0. 0 times 6 is?
0.
0.
Jesus.
So would we say that this is linear or nonlinear?
Linear.
Why? What are these going up by?
6.
Good. We're going plus 6 every time on those. So it is linear. Jada? How we got these y's? Is that the part?
Yeah.
Okay. So we plugged in the x's. So here we showed where we plugged in a -1. So -1 minus 1 gave us -2. Then we multiply it to get the -12. I'll take away this up here so I have more space. So then we moved on and we plugged in the 0 for x. So 0 minus 1 gave us a -1. And we multiplied that by 6 to get a -6. That's how that came in the middle. Last up, we plugged in a +1. So we had 1 minus 1, which is 0, and 6 times 0 is 0. That's how we got a 0 back there. So then after we do that, we see how the y's change. To get from -12 to -6, we would add 6. From -6 to 0, we would add 6. Since we had a constant rate of change, this was linear. Okay. Questions, concerns before we do the next one? Anybody have any thoughts about whether y equals 2 over x is linear or not?
Nah, man, yeah.
Why?
I don't know, I'm just guessing.
Just feeling. Anybody
Yeah.
else have a feeling about it?
I feel that it's just not linear.
Okay.
Me too.
Got a few feelings. All right, so I think this is another one that we could do by a table, and it seems like maybe we need a little more practice with a table. So let's put a table up here. So this is going to be for that y equals 2 over x down there. So let's plug in 1, and let's plug in, well, I'm having a bit of a harder time deciding what to plug in on this one. We can try 1, 2, and 3. It'll just be a little tricky. Okay, so if we plug in a 1, we have 2 over 1, which equals 2. Not so bad. The next one, what are we plugging in for x? 2. 2 over 2 is 1. What is currently happening to our y's? Just this first step, what do we do?
Subtracting 1.
Subtracting 1. So if this is going to keep going and become linear, we would want this to be what?
0.
A 0. But what are we plugging in for x?
3.
Does 2/3 simplify?
No.
No. Is it 0?
No.
No. So this is
Linear.
non-linear. Okay, we were adding 1 on top. We added 1. But on bottom we subtracted 1, and then we subtracted like 1/3. We subtracted a fraction. Either way, we should be able to tell that this is going to be non-linear. Yes, ma'am.
If you would use like -1, 0, 1 from the top, would it still like tell you it's like non-linear?
It would, but you run into an issue using 0 because you can't divide by 0. So you cannot, like even in a calculator, take 2 divided by 0. It tells you domain error or error of some kind. So it would be impossible to use 0. That's why I kind of paused a little bit when I was coming up with that table for us. So let me show you what the graph of that looks like, and you'll kind of see why, or maybe see why 0 is not an option here. Okay, this is the graph. This is not something that we would ever graph. But you can see this blue line, it happens up here and down here. Okay, a blue line here and down here. And at the 0, x equals 0, it doesn't actually ever touch the y-axis. It gets really close at the top and the bottom, but it would never actually touch it. So that's part of why you can't plug in 0 for x, visually at least. Okay, and also we can see from this graph that this definitely is not a straight line. Questions about that one? Okay, we've got one more that we need to decide. Our last one, x squared minus y equals 0. So real quick, before we do that one, if you're looking for a reason for why this one would be nonlinear, it's because x is in the denominator. So x in denominator will always be nonlinear. Okay. Can't have x in the denominator for a linear function. Now let's see if we can pop a graph of that last one up here. Maybe. Well, I'm going to have to rearrange it for Google to give me the graph, but I'll show it to you.
Excuse me.
Yes, sir.
Do you ever use the website Mathway to get the solution, or do
No.
you just use Google itself?
I usually use Google or a website called Wolfram Alpha.
Why don't you use Mathway? Is it because it's hard to see?
Nope, I've just never used it. Never needed to, Jada. Was our last problem. Okay. So this graph is going to be nonlinear. Now, you might see in my search bar up here that I had to type it a little bit differently than how it's shown, but that the x is still getting squared. So let's real quick talk about this one. It's going to be nonlinear The reason is because there is an exponent on x. So x cannot be in the exponent, and x cannot have an exponent other than 1. So our reason there would be x can't have an exponent. Ooh, ran out of space. Okay, so on this one, the only ones that ended up being linear were y equals 3.8 and y equals 6 times x minus 1. All the other ones had issues that made them nonlinear. Questions, concerns? Okay, the last thing in this slideshow real fast is representations of functions. There's really nothing for us to do on this page except you would want to fill in the equation that is being shown here. So this is on the very back of your notes, very last page. These are different ways that you can be shown a function and have to decide if it's linear or nonlinear. You can actually show other relations this way too and still decide if it's a function or not. But all of these illustrate y equals x plus 3. You'll notice that the input-output tables and mapping diagrams are very similar. They kind of line things up for us. And then the graph, of course, shows those points in a coordinate plane. Questions, concerns about different representations that we have seen? Okay. Your homework is in the textbook. It is on pages 117 and 118. 1, 2, 5 through 25, just the odds in that section, 5 through 25, and also number 26.